Okay, so in this video lecture, we're going to dig deep into one type of severe thunderstorm. You see, in order for a thunderstorm to be considered severe, it must reach one of these three criteria. The first is this. The storm must be able to produce winds in excess of 58 miles an hour. That's 50 knots. That's the wind threshold within a thunderstorm for considering that thunderstorm severe. Two, the thunderstorm can produce hail of 1 inch diameter or greater. You can see some of the world's largest hailstones ever on record, this being the second largest hailstone ever here at over 7 inches in diameter. Baseball size hail here doing some serious damage to this windshield, while any hail bigger than 1 inch in diameter is considered severe. The third and final thing is if the storm produces a tornado. And so you just need one of these three criteria in order for the thunderstorm to be considered severe. So it may not produce a tornado or strong straight line winds, but if it has hail, that's considered a severe storm. So you can see how that works. Now, the ultimate goal, as I've written down here at the bottom of any storm chase, is that after you've identified those four ingredients and you know where to pinpoint, kind of find your target for where the storms are going to initiate, the goal is to be able to watch the tornado very safely and avoid the hail and the straight line winds. Our focus today is going to be on the straight line winds. We're going to get to that in just a few moments. Now, it is the job of a group, part of the National Weather Service, called the Storm Prediction Center, to help us understand where in the United States on any given day we're going to see some severe weather. In fact, they do their severe weather forecasting out 8 days in advance to kind of hone in on regions where they expect to see severe weather. And they are very, very good. They are quite possibly the best severe weather forecasters on the planet. Now, before they started changing up the way that they did their maps, this was how they originally used to produce their SPC graphics. And what you see in the upper left-hand corner is what they call their convective outlook map. Now, for our class, just let the word convective mean thunderstorm. They break down their thunderstorm risk into a few categories. The old categories they used was a general risk for thunderstorms. That would be this outside arrow. Anything to the right of it meant that there was a general risk of thunderstorms. They'd go from the general risk to the slight risk, the moderate risk, and then the high risk. Those were the categories. Now, in the middle of thunderstorm season, you'd probably see a slight risk somewhere across the country, 6 days out of every single week. Moderate risks are a lot more rare. We may see them only come out, a handful of times a year, maybe 15 times a year do we have a moderate risk. And high risk days are very, very rare. They may only happen once, twice, 3 times a year. So each one designates a different risk level, and it's all broken down into percentages and therefore probabilities. So remember, 3 things to make a thunderstorm severe. Well, if we start up with this graphic and kind of blow it out to what it looks like, we have our tornado risk in this panel. We have our hail risk in this panel, and in the bottom one, we have our severe wind risk. So you can see the probabilities of each event occurring. Let's start up in the tornadoes here. When you look at this one, this green outline here, I think it's green on the outside here, tells us that there's a 2% chance of having a tornado within 25 miles of any given point. You see, that's what the probability is telling you. That means when you get in here to this center arrow here, that's in red, I think, that particular arrow says there's a 30% or greater probability of having a tornado within 25 miles of any given point inside of where that arrow kind of encapsulates. The hatching here, that means that there's a 10% or greater probability that we'll see a tornado that is a strong one, in EF2 or stronger. So this was a pretty insane day for Wisconsin, and I'll never forget it because I got to chase the storms that went through Wisconsin on this particular day. Now, we can take it down and look at the wind probabilities, read the same way. 45% chance of seeing winds in excess of 58 miles an hour within 25 miles of any given point. Hail, 45% chance or greater of seeing hail bigger than an inch. You see how that works? So again, spc.noaa.gov is where you want to go to see this. Now, the Storm Prediction Center has made a few changes over the last couple of years, and this is what some of their latest graphics look like. On this particular day, this was October 21st, Saturday, 2017, we can see that they have their general risk here, but they've added a few new categories. One is a marginal risk. Then they have their slight risk. Between the slight and moderate risk, there's now an enhanced risk. So what they've essentially done is added a few more layers to help us understand the relative levels of risk. What we can see is broken down into the tornado threat. Over here, we've got a 5% chance of having a tornado within 25 miles of any given point here, mainly in Oklahoma. Our hail threat down here, big time hail threat. You can see better than 30% chance of having hail within 25 miles of any given point, and a broad area of 30% chance or better of having severe winds over 58 miles an hour. So this is kind of a more modern look at what the Storm Prediction Center is showing. Okay, let's take this and try to dissect what all of this means. First, what is a watch versus a warning? Now, if someone ever invents this, I will buy one immediately. Like a watch that projects, a tornado over the top of like a hologram. That would be the coolest freaking thing I can imagine. So I want to make sure that everybody here understands the difference between a tornado watch and a tornado warning. It's very simple. A tornado watch means conditions are favorable. Well, what are the conditions? Those are the conditions we just learned about. It's the conditions of having an unstable atmosphere, a trigger mechanism, lots of surface moisture, and wind shear. That means we are watching for the potential development of a tornado. It does not mean that we're watching a tornado. If we're watching a tornado, then we issue a tornado warning. Okay? See the difference between a watch and a warning. Now again, those watches mean that either a severe thunderstorm or a tornado watch, we issue those when the conditions are present. So what are those conditions? Again, got to have plenty of surface moisture. Remember, our dew point temperature is above 60 degrees Fahrenheit. A lifting mechanism, like a front. An unstable atmosphere, like having lots of CAPE or a negative lifting index, and then lots and lots of wind shear. When you look at around the world at where we have our tornado watches, or I should say if you look around the United States for where we have our most frequent tornado watches, it's centered right down here, right along the Gulf Coast in the states of Louisiana, Mississippi, Alabama, Georgia, and then partly into Oklahoma, bits of Texas, and Arkansas. The reason why this region is highlighted, especially right down here toward the Gulf Coast, is because at any given time of year, this particular location can have tornadoes. So that's your tornado hotspot when it comes to tornado watches being issued. Over here, we're looking at severe thunderstorm watches. We can see that they're most frequent right here in the states of Oklahoma and Kansas. So that would be where we have the most frequent severe thunderstorm watches. All right, a warning means whatever type of severe weather you're talking about is happening at that moment. So tornado warnings can be based on a few things. One, if a tornado has been cited by an official, like a police officer or a trained spotter, then they will issue a warning based upon their visual inspection of the weather. We can also warn tornadoes by doing what's called a Doppler indicated warning. I got an example of that over here. In the upper panel here, we see a radar reflectivity image, very clearly defined hook echo, even some embedded hail in this storm. But it's the combination of seeing this hook echo plus this red-green velocity couplet right here that would indicate that this storm is capable of producing a tornado. When it comes to severe thunderstorms, don't forget that if we detect radar reflectivity values, so that's measured in dBz greater than 60, that indicates hail, so they'll be pinging that storm for a severe thunderstorm warning. If the Doppler radar sees winds over 50 knots, that's 58 miles an hour, or a weather station observes winds over 50 knots, which is 58 miles an hour, then they will warn that as well. Or finally, if a storm spotter or official, again like a police officer or firefighter, sees hail bigger than an inch, it will be warned as well. Now, what's neat about the advancements in technology is that we have switched away from doing a county-based warning system to a storm-based warning system in the last decade or so. You see, it used to be that if any particular part of a county experienced severe weather, they would warn the entire county. But now, because we can pinpoint with really good Doppler technology the exact locations where the severe weather is based, the ability to only warn those people that are directly affected is what we're now able to do. And as you can see from the graphic, that means 70% 70% less area is being covered by the warnings unnecessarily, and 600,000 fewer people are warned in this particular case study. Now, what that also means is that I know we kind of, in the past, don't always necessarily trust when the sirens go off, may think, okay, the sirens are off, but most of the times when they go off, the storm isn't going to hit us. Well, now that's different because we're doing storm-based warning. If the sirens go off, you need to take shelter immediately because we're much more accurate at pinning down where the severe parts of the storms are located. Now, it is also the job of the Storm Prediction Center to release maps like these. Now these are going back to the year of 2011, and they show you over that entire year every location where we had a tornado report, a severe wind report, and a hail report. They on average received somewhere between 20,000 and 30,000 reports of severe weather, and they map them just like you see here. Typical year for tornadoes, we have anywhere between 900 and 1,500 reports. Winds, quite a few more at 10,000 to 15,000, and hail kind of right there just below wind at 7,000 to 10,000. You can really see that, honestly, east of the Rocky Mountains, nearly every single location is going to experience something nearby in terms of tornadoes, wind, or hail. And it's not that we don't have severe weather out west, it's just that there are far fewer people in the Intermountain West to report this severe weather. Also, something kind of neat down here, you'll often see this little pocket of Florida never gets any reports, and that's because that's where the Everglades are, and people don't live there to report this severe weather. So it's kind of a neat thing to see how the population affects where we are reporting our severe weather. But here's our averages for each year. Now, I showed you earlier what the Storm Prediction Center's risk was on October 21st, 2017. And sure enough, in that same region where they had forecast for the enhanced risk of severe storms, 5 reports of tornadoes right in through here, 68 reports of winds greater than 50 knots or 58 miles an hour, and 30 reports of hail, 5 of which were 2 inches in diameter or larger. So they did a fantastic job kind of nailing down exactly where that severe weather was going to be. Remember, they'll do that prediction out 8 days in advance. So keep a close eye on spc.noaa.gov. All right, for the second half of this lecture, now that we understand what the Storm Prediction Center's role is, I want to talk about the type of storm that produces this cloud feature. It's a cloud feature that's commonly associated with the very strong straight-line winds of a storm system. It's the type of storm system we call the Mesoscale convective system. And along the leading edge of an MCS, we can produce some incredibly severe conditions. For example, the day that currently holds the record for the most severe weather reports happened on April 4th, 2011. On that day, there was one huge squall line, and we're seeing it every 3 hours or so, kind of progressing toward the southeast in this composite radar image here. It produced 1,476 reports of severe weather in a single day. When you look over here, there were 12 tornado watches, 12 severe thunderstorm watches, 104 tornado warnings, and 635 severe thunderstorm warnings in a single day. That is incredible to see how that all unfolded there on April 4th. Major, major, major weather event there. All right, quick question for you as you're watching this video. Check out the cloud in the background given me by one of my former students named Stephanie. My question is, what is this cloud called? Is it called a hinge cloud, a wall cloud, a pole cloud, a countertop cloud, or a shelf cloud? Now, clearly all of your options here have something to do with, things you might find in a house. But I want to tell you what this one's called. It's called a shelf cloud because it kind of looks like a shelf out ahead of the storm. We'll come back to what a wall cloud is very soon in our lectures on tornadoes, but this one's called a shelf cloud. Now, as a cloud like this one, a shelf cloud, passes over, what should you prepare to feel? Maggie sent me this beautiful picture of a shelf cloud. So would you feel a blast of very warm, humid air? Would you feel nothing? This cloud will pass over you and barely kick up a breeze. Or C, a violent, rapidly rotating tornado-like wind will accompany this cloud and cause a lot of damage. Or D, a gusty burst of cooler air. Now, you might be surprised to find out that when a cloud like this passes you, if you've never experienced one before, you'll get D, a gusty burst of cooler air. You see, this cloud forms as a part of the downdraft of the thunderstorm, and it is made on the outflow of that downdraft. And it's actually found right at the intersection where the downdraft meets the updraft, and that's a cool thing to study. All right, check out this video here along this beach of this massive shelf cloud moving forward. You can see it does look quite scary as it's coming over the horizon, and it's advancing toward them at about 60 miles an hour. Now, here's the lesson I want you to learn by watching this video. I don't want you necessarily acting like this girl. You can see she's clearly scared by it, and that's fine, and there she goes running off, kind of away from the storm system. Honestly, if one of these approaches you, I want you to act like the rest of the people on the beach, primarily this guy right here. You see, he must have taken Atmos 120 because what he's going to do is he's going to get his cell phone out or a camera out, and as it's approaching, he's going to get a picture of it. And honestly, that's fine if you want to do that, because this cloud is all bark and no bite. You see, as it comes racing over, yes, it looks ominous, and yes, it looks scary, but it's a warning cloud. It says, hey, when you see me on the horizon, you've got about 5 minutes to take shelter, because it's what's coming behind me that is the most severe part of any storm. There you just heard that same girl scream that you saw running off a few moments ago. If you get out and take a picture of it, send it to me. I want to put it in my lectures, because these things are amazing. Remember, it's what's behind the shelf cloud that is the most severe part of the storm. So again, they're your warning cloud. You got 5 minutes. All right. So what is this feature when it comes to learning about the squall line, or the Mesoscale convective system, MCS? What does that mean again? Mesoscale, that means small scale. Convective means thunderstorm, and system means that it's a group of thunderstorms. You see, along the leading edge of the squall line, or the mesoscale convective system, you have what's called a gust front. It's like a mini cold front made by the thunderstorm. It's a cool blast of air that kind of forms in the downdraft of the thunderstorm and races out ahead of it. I'll show it to you in just a few moments. Now, along that gust front, you'll make that cloud you just saw, called the shelf cloud. It's a large, low-hanging, typically non-precipitating cloud feature. Here's a few of my former students on a beach in Florida who just let the shelf cloud pass right over them. They were taking shelter moments after this. And here's a video taken by one of my friends, Jonathan Ramirez, of a beautiful shelf cloud coming over Champaign County several years ago. Again, amazing to see this. That cloud is all bark and no bite. As it passes over, it says, listen, a few minutes from now, the nasty part of the storm is on its way. Now, in the left-hand side of this screen, of our screen here, we have this huge squall line. Where do we find the shelf cloud? Where does this feature sit? Well, it sits right here. You see, it's right on the leading edge of the storm system. And these storms moving across central Illinois were coming from the northwest to the southeast. So that cloud feature would be found right here along the front edge of the storm. Okay, how does it form? Well, here's a shelf cloud. Let me show you how it works. You see, coming from the back side of the storm is the main downdraft, and it comes rushing out ahead of the storm just like this. Ahead of it, it lifts warm, moist, and unstable air. That forms clouds. And the shelf cloud forms as that warm, moist air goes riding right out over the top of this outflow. Now, don't ever confuse a shelf cloud and a wall cloud. Shelf clouds don't spin. They just advance forward like a big long line of deep, dark clouds advancing toward you. Remember, they're just a warning cloud. They're all bark and no bite. So let me give you an example of what inflow versus outflow is. You can see the shelf cloud here. Now what's interesting is that the air at this point, as indicated by the smokestack, was clearly moving in toward the storm. We had outflow behind the storm once it passed over, pushing the smoke the other direction. See that? So on one side the air flows in and up, and on the other side it flows out or down and out, just like this. And the smokestack was our indicator. Thanks to Zach, one of our former students, for giving me these pictures. On radar, sometimes you can even see the shelf cloud. Here's a set of thunderstorms that are passing over the St. Louis radar back in 2007, so a number of years ago. You see, the feature I want you to key in on is this fine line of radar reflectivity right here. That's the location of the shelf cloud. Now, what's neat about these storms is that the shelf cloud is actually outlasting the storms behind them. In fact, you're watching the storms dissipate. That's because these storms are moving across St. Louis at 4 o'clock in the morning, 4 or 5 in the morning. And during that time of day, it's too stable. We just don't have enough instability in the atmosphere usually to support strong storms that last all night long. It's not that they can't, but it's kind of rare. But again, that radar reflectivity fine line right out ahead of the storm system is how sometimes the radar can see the shelf cloud. Now, let me give you a more serious example of this. Here was a squall line that went through Indianapolis a few years ago in 2011. Out ahead of it, this is the radar fine line indicating the position of the shelf cloud. Now, as that radar fine line passed over this particular area, people saw it. They actually took pictures of it just like this. And as that shelf cloud passed over, remember, it's your warning. It says, hey, the nasty part of this storm is behind me. On this particular night, there was a concert being held at the Indiana State Fairgrounds. And I'm going to warn you, the video that you're about to watch next is graphic. If you do not want to see it, I suggest just fast forwarding through the next video. What we're going to watch is what happens after this shelf cloud, again, indicating the approaching outflow of that thunderstorm, the strong straight line winds of the storm, what it's going to do to this particular grandstand setup here. So again, the next video is graphic, but I would like to show you what happened in this event so that you'll never forget how to understand this type of cloud feature. So let's take a look. Tragically, because of this, 8 people lost their lives, crushed by that scaffolding. Now, the thing that I'm trying to bring to a point here is that the shelf cloud was your indicator long before that part of the storm arrived. Use your senses, use your knowledge that you've been given in this class to know how to recognize severe thunderstorm cloud types. And the shelf cloud is one of the first ones I've taught you this semester. So again, it is that shelf cloud that is your warning cloud. Now, what follows that shelf cloud, what made that storm severe, is often a section of the Mesoscale convective system, the MCS, which we call the bow echo. The bow echo is a region of very high radar reflectivity, which again indicates intense thunderstorms that bow outward in the same way that a hunter's bow makes a bow. So for example, in this part of the thunderstorm down here where it's pretty much a straight line, we don't have too much in the terms of strong severe winds. There's certainly some embedded hail. See the radar reflectivity over 60 dBz there and there. But this section of storms will be different from this section because of the way it bows. It gets its name because it looks like a hunter's bow. When drawn back under the tension of the string, the bow will bend. And just like how you don't want to be at the apex of a hunter's bow where the arrow comes out, you don't want to be at the apex of the squall line in the bow echo right here. It is along this feature that we have very strong back to front flow called the rear inflow jet. A rear inflow jet forms in the back of the storms and dives down and descends here in the back of the storm and hits the ground and spreads forward, sometimes with wind speeds that get over 100 miles an hour. So if you're ever looking at a radar reflectivity image and you start to see a squalling of thunderstorms making a bowing feature just like this, know that along that bowing feature, you are going to have very strong straight line winds. So for example, here's another example of a squall line, a MCS with a bowing feature on it. Right here at the apex of the bow is where you want to avoid. That was what came over that grandstand that you just saw in the previous video. So these are the kinds of storms that do that. So the front edge has the shelf cloud and the gust front. Following that, oftentimes, is the most intense part of the storm called a bow echo. And what happens is after that passes, you have your third type, a third feature that comes behind the storm. It's called the trailing stratiform region. Trailing meaning following, stratiform meaning layered, and region meaning it's occupying a large section of the storm. It's this spot behind the storm where you get a bunch of light to moderate rain that follows the intense leading edge of the storm. If you ever notice that after the really nasty part of the storm goes over, you often get maybe an hour or two of just lightning and thunder and moderate rain? Well, it's this part of the storm. You see, the leading edge is here, but behind it is this kind of light to moderate rain that just hangs out there for a while. It's occurring in this part of the storm and looked at in terms of a cross section. So it's kind of a neat thing to see here. Lastly, sometimes these storms tend to curl up on their northern end. We call that a bookend vortex, like you see right here. It's just the northern side of the storm curling due to the flow, the dynamical flow of this storm, causing it to kind of bend around on the back side here. And it's been occasionally found that very, very weak tornadoes might form inside of the bookend vortex. But I want to show you what the main edge of this storm system looks like. We also have to watch the front edge of the mesoscale convective system for the development of what we call gust-nados. These are tornadoes that form very weakly right along the leading edge of a squall line. I'll show you what some of those look like when we get into our lectures on tornadoes. So, couple of fun questions as some review here. So here's my first question. Which of the following is not a requirement for a thunderstorm to be considered severe? Do you think it's A, frequent cloud to ground lightning, B, hail larger than an inch in diameter, C, tornado winds or thunderstorm winds in excess of 58 miles an hour, or D, a tornado? Well, the answer to this one is A, all thunderstorms produce cloud-to-ground lightning, so we can't use that as a criteria. The criteria we use: hail bigger than an inch, winds faster than 58, or a tornado. Let's try another one here. Below are the conditions on a day in May. The National Weather Service did not forecast severe thunderstorms on this day. Why? Was it A, the lifted index was +4? Was it B, the dew point temperature was 71? Was it C, there was a cold front that was coming through the region? Or was it D, the winds near the surface were 10 miles an hour, while the winds in the middle atmosphere were 60? Let's start from the bottom. If we have a 10-mile-an-hour wind at the surface and a 60-mile-an-hour wind in the middle atmosphere, that's wind shear. That's a criteria we do need for severe thunderstorm development. What about the next one up? There was a cold front that was coming through the region. Well, a cold front's a trigger mechanism, so that is certainly one of the ingredients that we need. What about B? The dew point was 71 Fahrenheit. Now remember, when I chase, I look for dew point temperatures in excess of 60, so 71 is juicy. The problem here is that the lifted index was +4. We need a negative lifted index when we're talking about severe thunderstorm development. So that's the answer to that one. And I got one last quick fact recall question for you. On average, how many severe weather reports does the Storm Prediction Center receive each year? Well, as you're looking through your options there, remember that they receive between 20,000 and 30,000 a year. And that makes the United States one of the most kind of prolific, one of the regions with the most prolific thunderstorm events on Earth. We live kind of in a hotbed of severe thunderstorm activity, 20 to 30,000 reports a year. As one last thing to show you, I want to show you a radar animation of kind of a squall line that passed through Chicago a few years ago. Now, this is a little bit interesting case study here because on the left, I have animating the radial velocity imagery, and on the right, I have animating the radar reflectivity. We actually had two little mini bow echoes. You can see them, the one on the southern side, which is this one, and the one on the northern side, which is this one, and they kind of joined forces over the southern tip of Lake Michigan. Now, each one was producing winds in excess of 58 miles an hour. In fact, do you notice how as the storms go past the radar, where because they're moving away from the radar, we should see red coloring, that these green patches show up? What has happened here is that the winds in the storm are so fast that they've run out of the red colors and they've had to switch over to use the green colors. We call this folding. So this is radar radial velocity data that's not been de-aliased or unfolded. And that just tells me that the winds along the leading edge of these storms were probably in excess of around 80 miles an hour, maybe even faster than that. They certainly did a lot of damage. Here were some pictures sent to me from my students that live in the Chicagoland area. Those storms, which started off in Iowa, went across the Quad Cities area through northern Illinois and eventually over into Indiana and Michigan, produced 184 separate severe wind reports. You can see all the huge trees knocked down in Chicago. In fact, the Tribune reported after this on August 23rd, 2007, that over 4,000 trees were down in Chicago streets. Well, the Storm Prediction Center nailed it. They had this entire region out for a slight and even moderate risk the day before this event ever even happened. So pretty amazing to see this kind of severe weather so well forecasted by the Storm Prediction Center. So with that, I think you now got a better handle on what it is to see the mesoscale convective system, how it produces its shelf cloud, its bow echo, and its trailing stratiform region, and how it contributes to the most common type of severe weather in the United States, strong straight line winds. With that, I'll go ahead and wrap up this lecture. Thank you for watching.